Hello everyone, welcome to this short webinar where I will present some results from the past GlobCoast and ongoing CO2 coast projects, illustrating how Ocean Color Radiometry can help us to monitor the global coastal waters. These two projects have been funded by the ANR, which is the French research agency. So one of the main issues in the use of ocean color radiometry for the monitoring of coastal waters relies into their physical and bio-optical complexities, making their observations from satellite very challenging. Because the atmosphere may contribute up to about 80% of the top of atmosphere signal recorded by the sensor, atmospheric correction has to be done to estimate the marine signal, called the remote sensing reflectance. Then, bio-optical algorithms using RRS have to be developed to estimate the different biogeochemical and optical parameters. Among them, we can find the chlorophyll concentration, the suspended particulate matter, absorption by color dissolved organic matter, or partial pressure of CO2 and many other parameters. So while many improvements have been done for about 2 decades by the ocean color community in terms of algorithms development for the monitoring of coastal waters, the application of these algorithms is still limited to local or regional scales. The common feature of the GlobCoast and CO2 Coast projects is that they both deal with coastal waters at global scale. So two different statements have motivated the development of this project. For GlobCoast, it is that the temporal pattern of the surface bio-optical properties of coastal waters have still not been characterized at global scale. Then, the main objectives of this project were the assessments of the temporal variability of biogeochemical properties of the global coastal waters, and then the analysis of this temporal variability as a function of physical forcing parameters as derived from remote sensing, in situ measurements, or modeling. For CO2 coast, the main goal is to address the fact that the net uptake of carbon in the coastal margin remains a poorly constrained term in global carbon budgets. The objectives of CO2 coast are first to estimate the surface ocean CO2 partial pressure and CO2 fluxes at global coastal water over the global coastal water at 1 square kilometer, which is quite high compared to the products which are right now available, which are at the spatial resolutions of about 30 square kilometer. Second objective is the assessments of the seasonal, interannual, and last 25 years trend evolutions of these parameters. And at last, the analysis of the respective contribution of estuaries on coastal shelf water, as well as the contribution of the different continental shelf types. So the GlobCoast project focuses on the data collected by a unique sensor, the MERIS sensor, between 2002 and 2012 to avoid any artificial bias. However, the methodology and the algorithm which have been developed can be applied to any ocean color sensors. The descriptions and analysis of the spatio-temporal variability of the different parameters at global scale require adapted tools. So, for instance, the temporal patterns are analyzed using the Census X11 method, which allows the irregular, seasonal, and trend contributions to the variance of the temporal signal to be extracted. You have here an example showing the map of the seasonal contribution in percentage for the suspended particulate matter variability over 10 years. For example, a red area means that in this area, 80% of the temporal variability is driven by the seasonal component. Correlation maps between the different products and forcing parameters are used to identify the processes at the origin of this variability. You have an example here at the outlet of the Mekong Delta between SPM and waves and swell, and where high air value depict erosion and resuspension areas where waves and swell control the SPM variability, and low air value reflects the regulation of SPM loads by river discharge. The long-term trends using the Kendall slope, which is expressed in percentage per year, allows hotspot to be identified at global scale. So this figure is the global trend of suspended particulate matter over 10 years, showing that 7% of the coastal zone, of the global coastal zone, show a significant SPM long-term trend variability. Among them, 70% exhibit a decrease, more than 2% per year, but strong increasing and decreasing trends are balanced. So the different terms may directly provide information on natural processes affecting the distribution of the parameter. For example, here on the left side, you have the map of the Kendall slope, showing that the Kendall slope patterns of SPM along the French Guiana coast exhibit a succession of increasing in red and decreasing in blue areas, illustrating the migration, in fact, of mud bank coming from the Amazon River estuary. On the right side here, you have the contributions of the irregular component of the variance of the SPM time series, again over 10 years, showing that the maximum, the high contribution of this irregular term is located where the frequency of eddies here is maximum. This result stresses that submesoscale processes control the SPM variability in this area. So to estimate PCO2 over the global coastal ocean, the CO2 Coast project combines through different advanced algorithms an exceptional in situ dataset of PCO2 in situ measurements coming from the SOCAT database, long time series of satellite data coming from OCR, SST, ice cover, wind speed, and knowledge from specific modeling and experiments which will be performed during the project. So here you have the number of data points available on this database, 11 million, and the number of matchup with ocean color sensors, which is about 500,000. So the relatively high spatial resolution used in the frame of CO2 Coast will allow to cover a large number of estuaries, about 81%, references in Alder and Watson et al., allowing to estimate their contributions to the CO2 fluxes versus the contribution of continental shelves to the CO2 fluxes. So preliminary attempts to estimate PCO2 over global coastal waters clearly show the advantage of a class-based neural network approach compared to a global network algorithm. This is shown here on the validation exercise over the eastern coast of the US, and using the global-based neural network, and here's the global classification-based neural network, which allow to recover much more data points. In the same way, on the right side, preliminary results show that the methodology adopted provides good PCO2 spatial patterns, which is illustrated here, with a good agreement between the in situ measurements here and the estimation from satellite. To summarize this short webinar, I would say that the monitoring of bio-optical parameters from ocean color remote sensing, combined with physical forcing parameters and integrated in a proper matrix, provide pertinent information on the evolution of coastal waters as well as on some relevant coupling processes. Thanks for your attention.